Look at any photo on your phone. Shrink it, blow it up. The shape never changes, only the size. That one idea, same shape but different size, is called similarity, and it's the secret behind measuring the height of a mountain without ever climbing it. Today we'll nail down exactly what similarity means, then meet a 2,000-year-old theorem from Thales that quietly powers this whole chapter. Let's build it. Two figures are similar if they have the same shape, but not necessarily the same size. The same photo printed small and large. Now, if two figures have the same shape and the same size, we call them congruent. Congruence is the stricter idea. Same shape and same size too. Here's the relationship to lock in. Every pair of congruent figures is also similar. Same size is just a special case of same shape. But the reverse is not true. Similar figures need not be congruent. And some shapes are always similar because their shape never changes. All circles are similar, all squares are similar, and all equilateral triangles are similar. So when are two polygons, say two quadrilaterals, similar? Two things must both hold. 1, their corresponding angles are equal. 2, their corresponding sides are in the same ratio, proportional. Miss either one and they are not similar. And the order matters. You must match the vertices in the correct correspondence when you write the similarity. Why insist on both? Watch. Take a square and a rectangle. All their angles are 90 degrees, so corresponding angles are equal. Condition 1 holds. But the sides aren't in the same ratio, so condition 2 fails and they are not similar. Now take a square and a rhombus. All sides equal, so the sides are in the same ratio. Condition 2 holds. But the rhombus's angles aren't 90 degrees, so condition 1 fails. Again, not similar. For polygons, one condition alone is never enough. And that common ratio of corresponding sides has a name, the scale factor. A map, or a building blueprint, is just the real thing drawn to a scale factor. A triangle is a polygon too, so the same rule applies. Equal angles and proportional sides. But triangles are special, and it starts with a result the Greek mathematician Thales discovered. Draw any triangle ABC. Now draw a line parallel to one side, parallel to BC, cutting the other two sides at D and E. Thales' theorem, also called the Basic Proportionality Theorem, says that parallel line divides the two sides in the same ratio. In symbols, AD over DB equals AE over EC. Where does that come from? A slick area argument. Join BE and CD to make two small triangles, BDE and DEC. They sit on the same base, DE, and between the same pair of parallel lines, DE and BC, so they have equal areas. Now compare each with triangle ADE. The ratio of the areas ADE to BDE works out to AD over DB, and the ratio ADE to DEC works out to AE over EC. Since BDE and DEC have equal areas, those two ratios must be equal, and that's exactly AD over DB equals AE over EC. A handy second form, if DE is parallel to BC, then AD over AB also equals AE over AC, the whole side instead of the piece. Use whichever fits your numbers. Let's try it. DE parallel to BC with AD 2 centimeters, DB 3, and AE 4. Find EC. By the theorem, AD over DB equals AE over EC, so 2 over 3 equals 4 over EC. Cross multiply, 2 times EC is 12, so EC is 6 centimeters. No ruler, just the ratio. Now flip it. The converse is also true and just as useful. If a line divides two sides of a triangle in the same ratio, then it must be parallel to the third side. This is how you prove two lines are parallel. Show the ratios match. Quick test. A point E on one side gives PE 4 and EQ 4.5. A point F on the other gives PF 8 and FR 9. Is EF parallel to QR? Check the ratios. 4 over 4.5 and 8 over 9. Both equal 0.88. They match, so yes, by the converse, EF is parallel to QR. Two famous results drop straight out of this. First, a line drawn through the midpoint of one side parallel to another side bisects the third side. Second, the line joining the midpoints of two sides is parallel to the third side. Both are just Thales and his converse in disguise, and you'll use them again and again. Time to test yourself. Here's a question on screen. Pause if you need to, but try it first. 10 seconds on the clock. Go. Use the theorem AD over DB equals AE over EC. Plug in 1.5 over 3 equals 1 over EC. The left side is 1/2, so EC equals 2 centimeters. That's option B. If you got it, the Thales ratio is genuinely yours. Let's lock it in. Similar means same shape, maybe different size. Two polygons are similar when their angles match and their sides are proportional. And Thales' theorem says a line parallel to one side of a triangle splits the other two in the same ratio, with the converse letting you prove lines parallel. One more before you go? It's on the screen. Don't say it out loud. Type your answer in the comments and I'll pin the correct one. Next video, we turn similarity into a toolkit. 3 quick criteria, AA, SSS, and SAS, that prove two triangles similar without checking all 6 parts. It's how you find the height of a tower from its shadow. Subscribe so it lands in your feed. This is Clarix. See you there.